Hi everyone and welcome back. So now we're going to be going over something called normal strain. And like this entire class sounds like some sort of torture device. First it was stress, now it's strain. Why do we have to learn about these things? Well, I think the engineer who created these terms was very stressed and strained at the time, and he's just like, you know what? That's what I'm going to name it. Stress and strain. But okay, I have a terrible sense of humor. We're going to learn about strain today. Now, before we actually get into what strain is, let's go back to our bridge example and ask you one more question. So we have these wires, and we now know we can figure out, well, how much stress they can take, and therefore, if we know how much stress they can take, we can figure out what loads they could hold. But let's look at it differently. Maybe you don't know what the stress inside of the wire is, or maybe you know what the stress it can take is, but you don't know the load. You have no way of calculating it. All you can ever do is just physically observe it, okay? So you watch it, and you see it stretching, you see it contracting back again, stretching and contracting back again when you take the load off and put it on. Do you think there's a way we can determine how far they can stretch before failing? That's probably important. Do you also think that the dimensions of the wire matter for this? Like, is the thickness going to matter? Is the width going to matter? That's something we should figure out. Okay, going back to these boats, they connect boats to the dock, and we want the boats to be able to move a little bit, because these ropes are usually somewhat elastic. However, if this is your boat, and there's a boat next to it, you do not want the rope to be able to stretch from here all the way over here so that you collide with that boat. That would be a bad thing, okay? Rope should not be able to stretch that much. So do you think if you knew what the load was from the boat, like the max load it might pull on that rope, could you figure out a way so that rope doesn't stretch that far? Like, maybe you have to use a certain material. Like rubber might go that far. Metal, probably way too strong and heavy. We have to think about this. And to do that, we're going to introduce a new concept today, which is called strain. Okay, so first off, displacement, deformation, and the concept of strain, okay? Now, how an object deforms under load is equally important as stress. Now, remember, in all of our previous classes, we had boxes and planes and everything else. We applied forces to them, and that was it. The box is always magically perfect. It's impervious. It can't be changed. We always called them rigid bodies for a reason. Solid mechanics, no more rigid bodies. They can and do deform. So we need to understand how those internal forces affect real bodies. Now, when an applied load does not change the relative position between any 2 points, that's that whole rigid body thing. Right now, we moved it, we turned it a little bit, but it was rigid body displacement. This class, though, we're not really going to deal with that as much, okay? We're not going to deal with that as much. What we're going to be dealing, though, is deformation. It's where the vector between points h and k in some particular material, well, that changes. That vector, that relative vector between those 2 points in the body, after deformation, it's going to be different. They're going to have stretched or contracted. They're going to move closer or further apart. So this can be caused by your applied loads. It can also be caused by temperature, which you should never forget, because temperature is something that affects everything in the world. I mean, some bridges grow an entire foot, sometimes several feet, depending on how long they are, on a hot day versus a cold day. And you've got to make sure that there's room for it to have that growth and room for it to contract without people falling into some terrible, terrible gap. It'd be pretty bad if you're like, well, on the hot days, these 2 pieces of road, they touch. On the cold days, a gap opens up and, well, sadly, people fall into the cliff. Ooh! I think you might want to look for a new job. And you might be getting sued. But you are taking this class, and so hopefully you'll come up with some ideas on how you can keep people alive. Now, the change in any dimension after these applied loads is known as deformation. We have deformed this body. It is no longer the same as it was before. Under normal conditions, deformations are not uniform. They're not going to happen in the same way in every single direction. It just doesn't make sense. Like, if you have a ball and you squish it from the top, well, it gets wider and flatter. It got thinner in this direction and it got wider in that direction. It's not the same in every direction. Now, strain is a way to measure the intensity of a deformation, and we normalize it by the original length. Let me see. Yes. And just as there were normal stresses and shear stresses, there are also normal and shear strains. And guess what? They're connected. The normal strain is caused by normal stress. The shear strain is caused by shear stress. And there also is some interconnection in there. So it's not just perfectly only one is causing one thing. Now, one thing I really want you to remember though is when I said intensity earlier with stress, I was saying we had to normalize things. We took our force and we normalized it by the cross-sectional area. We're going to do the exact same thing with strain, okay? We're going to normalize it by its original length. But for now, we're going to stop here. And next time, we're going to jump into this concept of normal strain. So I hope this helps you. And next time, we're going to have some fun talking about normal strains and how those are calculated. So thank you for listening. I'll see you all next time. Bye-bye.